Okay, I think we can start now. You allow me to start, right?
Yes, sir.
Okay, so the others who are going to find us on the way. So the last time we met, I gave you one example. We were looking at the integrated rate law. We were looking at this law here, or this, we were looking at this equation here. So this is an equation for the integrated rate law. And then we did look at an application to that. So I gave you a question, which was an example. So I gave you an example, which we did. The example was here, okay? I'm just trying to recap on where we ended. So the example was this one that is here. This was the example, and we solved this example. Can you please put your mics on mute? We can get some feedback. Okay, so this was the example I ended up with, and we solved it. We solved this example. We ended at this point here. So just like I said, there are graphical methods. Okay, so using a graphical method, you can also look at one of the graphs that I gave you earlier was looking at the integrated rate law for the first order. Okay, so for a first order reaction, this is the equation. Take note, this is the equation. And this equation that I've shown here is an equation of a straight line. This equation is an equation of a straight line. Okay, so when I move to the next page, just bear with it so that you see properly what I mean. This is an equation of a straight line. And what that means is that this part here, the first part, is what is called the y. Remember that an equation of a straight line is written as y is equal to mx plus c. This is an equation of a straight line. So the y in this case is this guy here. Natural log of a at time t gives you the y. Then the minus k here gives you what the gradient is, okay? And then the t here gives you what the x, or what you are plotting as your x-axis. Then this whole thing here gives you what your y-intercept is. So when I go to the graph, you see that a plot of the natural log of time, the natural log of concentration at time t, against time, which are all in this equation. You can see the time is there, which is the x-axis, and the y-axis is there, which is the natural log of a at time t. I get a straight line. You can see the straight line with a negative slope. You can see the k here has got a negative value. So if I have data for negative natural log of time at time t, and I have data for time, I can plot a graph similar to what you are seeing on the screen. And then the slope of the line, if you calculate the gradient of the line, it will be equal to minus k. This is how you find the rate constant using the graph. Then the y-intercept gives you the natural log or the initial concentration of A. So this is what the integrated rate law for a first order tells us, or what it gives us. So sometimes you might be given data for time and the concentration. So you have to change that data to calculate the natural log of concentration versus time. And when you plot it, you're able to get the rate constant. So I think I've put up an example down here. You're going to see that. Okay. The example was, okay, it's far away. I'll show you the example. Related rate law for the second order reaction. So remember that for a second order, the rate we said is equal to, the rate is equal to K times the concentration of A to the power 2. That's how we said the rate was, okay? This is how you calculate the rate, okay? Then we also said that rate can also be written in terms of the change in concentration, the change in concentration of A divided by the change in time. So this is how we write the rate law: change in concentration divided by change in time, or you can use the rate law in terms of K times concentration of A to the power 2. So all of these are called rates. So if I combine these two, then I end up with what we have here, okay? Where I've just, instead of putting the change, I've put a D here, and I've also put a D here for the change there. So you can see that if I combine these two, if I put a D here and I put a D there, then I combine, I end up with this equation here, okay? So rate is equal to the change in concentration divided by change in time, or which is equal to K times the change in concentration of A to the power 2. So that gives you the rate equation. So now picking from here, I can integrate these two so that I remove the D's that you are seeing here. So I pick the right, the like terms together. So, and then I integrate on both sides. When I do that, I'll spare you the integration part. When I do that, I end up with this equation here. Similar to what we had as the integrated rate law for a first order, this is the integrated rate law for a second order. So you're talking about the integrated rate law for a second order. This is how it looks like. If you know that your equation is second order, the integrated rate law is given by this equation that is given. Again, this equation is an equation of a straight line, just like we did or we had with a first order reaction. This is an equation of a straight line, where in this case, the y-axis is this whole term here, 1 over concentration of A to the power at time t. This gives you your y-axis. Then your gradient, which is your m, is the same as k. So you can see this time the gradient is a positive gradient. Then your x-axis, which is a t, is your x in that case. Then your y-intercept is 1 over the initial concentration of A. So this is an equation of a straight line. Wilson, can you please switch off your mic? Okay, so this is an equation of a straight line. So what we mean is that now when you plot a graph where your y now is 1 over concentration of A, not natural log, concentration of A at time t, and then your x-axis is the time. You should get a straight line, okay, with a positive gradient, where the slope of this line, the gradient of this line is equal to the value for the rate constant. And then your y-intercept, where your graph touches your y-axis, will be equal to 1 over the initial concentration of A. And you are seeing from here that if your equation is a straight line, if your equation or your rate of reaction is a first order, it is only this plot that will give you a straight line. For a first order, it is only this plot that will give you a straight line. If your reaction is not a first order, then a plot of natural log against time will not give you a straight line. It's only for a first order. If the reaction is first order, that's when you can only have a straight line like that. If your reaction is not first order, you will not have this kind of graph. If your reaction is second order, you have a reaction or you have a graph with a straight line as shown on the screen there. This is for second order, okay? Second order reaction. If your reaction is not second order, it will not give you a straight line like this. Only reactions which are second order will give you a graph which is a straight line. Okay, so this gives us a basis or another way of determining or knowing the rate of reaction for a given chemical reaction, given that you have the graph. So you can use the graph to determine the order of reaction. You can plot that. So let me give you an example of how a question might be raised or might be framed if they want you to use the integrated rate law graphs to come up with the order of reaction. Okay, okay. So now this is just speaking about the same thing. I've already spoken about this. So this is the equation we've been dealing with. This is the equation we've dealt with. Okay, and this one is for the first order. You can see this is for a first order. This is for a second order. These are integrated rate law. For a second order, what we are plotting is 1 over concentration at time t. We are plotting it against t time. For a first order, you are plotting natural log of A at time t. You are plotting it against time. And the gradient of the line gives you, it will be equal to minus k. For a second order, the gradient of the line will be equal to positive k, which is the rate constant. So you can determine the rate constant by just calculating the gradient of a line. Okay. So now coming to an example, here is an example. Let me just rub what I've written on the screen. So I've already shown you this graph. I did draw this graph. I've shown you this graph already. So this should not be a problem. I've shown you this graph already. It's coming from the same equation that you have, which is an equation of a straight line. So I want to go to an example, which is this one here, okay? So let's look at this example here. You have an equation or a reaction where you have got nitrogen dioxide and it is decomposing to give you nitrogen oxide and oxygen gas. So this is the equation. So someone did an experiment and was collecting the decomposition of this gas at 300 degrees Celsius and came up with this data. This is the data that they came up with. The question is, what is the order of this reaction? What is the order of this reaction? Okay, so for us to know the order of this reaction, remember from the graphical point of view, I've given you different types of graphs. I've told you that you can have a graph of concentration versus time. Okay. If you have a graph of concentration versus time, for a zero order reaction, concentration versus time, for a zero order reaction, it will give you a straight line like this one. I showed you earlier, okay? If it's zero order, it will give you a straight line. So you can distinguish just from this data, you can plot concentration versus time. If it gives you a straight line, like the way you have seen here on the board, then you know that this reaction is zero order, okay? You know that the reaction will be zero order. If it does not give you a straight line, then you know that it's not a zero order. So you have to try the first order graph. For a first order, a plot of concentration versus time, it gives you a curve. And for a second order, it also gives us a curve. But for this one, it is very difficult for us to prove unless if there are two, like the way they are here, then you know that the one that at the bottom is first order, at the top is second order. But if it is one, like the way you are given here, just one set of data, you are definitely going to get a curve like this one, but you will not know whether it's a second order, okay, or it is a first order. So the second set of graphs that I gave you is where you are plotting rate. You remember I gave you a graph where you are plotting rate against concentration, okay? But in this question, we are not given any rate here. We don't have any rate. What we have is just concentration and time. So we cannot use this graph to determine the order of the reaction because we don't have the rate of reaction. So this one is out. So the other way now is what we have been learning, or where you use now the integrated rate law. So for integrated rate law, we know that we have learned two of them so far. We've learned two of them, the first order and the second order. We've learned about the first order and the second order. So for the first order, we know what to plot. For a first order, to prove if this is the first order, you need to plot a graph of natural log of A versus time. And if it gives us a straight line with a negative slope, then we know that this data belongs to a first order reaction. Okay, we can also try, if it doesn't give us a straight line, then the next thing is that we are going to try the second order data or kinetics, where we are going to be plotting 1 over the concentration against time. If it gives us a straight line, then we know that it's second order. So for this data, it will accept, or it will be in harmony with one of these, not both of these. So we have to try this data for both curves, for this and that, okay? We have to try it for a second order. We have to try it also for a first order. One of them is going to agree, then we are going to know that this is a second order or this is a first order. So trying the first order, let's now try this data for a first order. If you want to plot for a first order, then what it means is that we have to calculate the natural logs of concentrations. So we have to convert this concentration and calculate the natural log. So we extend the column here, we put another column, okay? We put another column where we say natural log of concentration of NO2. Then using our calculators, we can punch in and find values and fill up the table here. So we calculate the natural log of each one of these, natural log of this, natural log of that, natural log of that, and put up the data here. So we are going to do that. So here, I think I did that for you. Let me just move to the next point. The next slide. Let me just rub off this. So going to the next slide, you can see that I've extended this table and I've calculated the natural log of the concentration for the nitrogen dioxide. And these are the values here. You can see the values there. Okay. Then now I'm going to plot the natural log versus time. And I check whether it will give me a straight line like the way it is for a first order. So if I do the plot, this is what I get here. So I've shown you here what I'm getting now, okay? This is what I get. Okay, so this is what I get here. So you can see that from the plot, this is not a straight line, it is a curve. So what that means is that my data does not fit the first order kinetics. So this reaction is not first order. I hope you are getting that. So this reaction is not first order because a plot of natural log against time is supposed to give me a straight line if the reaction was first order. So for this reaction, it is not first order. Okay, so I have again to try this for a second order kinetics. Now, what am I supposed to plot for a second order? For a second order, what I'm supposed to plot is 1 over the concentration, okay, against time. So the inverse of the concentration. So what that means is that I extend the table here again, and I calculate the 1 over the concentration. I calculate 1 over concentration, I put in the value there, I calculate the inverse. Then that data, I'm going to plot it now against time and check whether it will give me a straight line. Okay, so this was also done. So I will rub off this. This was also done. So we are saying this graph does not fit first order. We are saying this graph does not fit the first order integrated rate law. So we have to try it for the second order. So for the second order now, this is what we have here. So I've calculated the 1 over the concentrations. These are the values here. You can see them here. So I'm now going to plot the 1 over concentration. I plot them against time. You can see from there. So now when I do that, this is a graph that I get here. So you can see that this one now fits exactly to a straight line. You can see the points are fitting in the exact way, okay, that was described. So therefore, this equation or this data here fits second order kinetics. So that reaction is second order. It follows the second. So you can see how it fits here. So if I calculate the gradient of this line, then I'll get my value for the rate constant. If I calculate the rate gradient of this line, I'll get the value for my rate constant. Any questions so far?
Yes, sir, there's a question. Your arrangement on the previous graph, I don't know if you can just get back.
This one?
So on the natural log values there, the arrangement, is it okay whereby start from negative 4.6 then going upwards, or start from the
So when you look at your graph paper, it has got 4 quadrants, right?
Yes.
We are together?
Yes, sir.
Hello? So
yes, I can get it.
So the y-axis, these are the negative values down here. Okay? These are the negative values for the y. These are the positive values. Now, when you look at my data that I have, my y-axis are negative values. You can see that. Hello?
Yes, sir.
Are you following? You are following?
Yes, sir. Yes, sir.
Yes, so now the plot that I've shown you here only looks at this quadrant here. So my 0 is here, my 0, 0 is here. And I'm just looking at this quadrant here. But instead of putting my y-axis on top here, my x-axis on top, I've just brought it down here. This is what you are seeing here. This is what you are seeing here. The 0, 0 is supposed to be here, 0. Supposed to be somewhere here. Then this becomes your y-axis, your x-axis, where you have time here.
Okay, all right, sir, I understand.
You have understood, no? Okay. Any more questions? Anyone with a question? Anyone with a question? So there's something.
Sir, so what formula are you using to get the values, those values for the negatives?
But second order kinetics using the integrated rate law. Integrated rate law for the last one, which is basically the zero order, Let me just rub off the board. So the zero order is easy because on this data, when you plot a graph of concentration versus time, zero order let's not the zero. The zero order rate law in the zero order. So for the zero order, again, we know that the rate is given by this equation, then the integrated rate law, the rate in this way. Then when you combine these two, you have this equation here. When you integrate this equation, this is what you come up, and this is what I want you to take note of. This is the zero order integrated rate law. What this equation tells you, this is also a line where this is your y and this is your m here. We have the x here, and then we have got the y-intercept there. Okay, so this is your y. So what are you plotting for a zero in the concentration versus here is for the x-axis versus time. And what you get is a negative with a k. So you get a curve, get a graph, which is a straight line like that, with a slope of this line being equal to minus k. So this gives you the integrated. For the zero order, all you have to plot is concentration versus time. And when you get a negative, it proves to you that the reaction is zero. Okay, so this one is straightforward as well. Okay, so let me go to the conclusion on the integrated rate law so that we can for now. Okay, so this is for the zero order. I've already shown you this graph. It's on the left screen there. So for the zero order, all the concentration versus time, it will give you with a negative slope, where the slope of this line gives you the rate constant. Calculate the rate constant also from the integrated rate law. Okay, so in summary now, okay, in summary, here is just another set of data. Suppose you are given this data, okay? Suppose you are given this data, time and concentration for the decomposition of N2O5. Then a question is asked, can you determine the order of this reaction? The order of this reaction. So you need to draw graphs, not one graph, but graphs. So you can start you can start with a zero order where you are plotting these two. And if it gives you a straight line, then you know that the rate of reaction or the kinetics was zero order. Then if it doesn't, you plot this against this. Okay. If it gives you a straight line, then it means it's a first order. If it doesn't, it means it's not a first order. Then you try also this and this. One of these will give you a straight line. Then you know that my kinetics was the second order, zero order, whatever it is. So using this data now, plots were done. So I'll show you the plots. So plots were done using this information that has been given. So concentration versus time was done. Natural log of concentration versus time was done. And also 1 over concentration versus time was also done. And these were the 3 graphs that were which one will be the order of that reaction or the decomposition of dinitrogen pentoxide? What is the order of that reaction? You can see plotting for the zero order doesn't give you a zero order. Plotting for the second order does not give you a straight line. But when you plot for the first order, it gives you a straight line. So meaning that this equation or this reaction is first order reaction. So this is how you get to know the order of reaction. So you have to plot graph by graph and see which one gives you a straight line. Sometimes they'll give you the order. They'll tell you that it is suspected that it is first order. Can you prove that it is first order? So you just go straight to the plot for the first order and check whether it gives you a straight line. If it does give you a straight line, then you say, yes, it's a first order. If it doesn't, then you say, no, it's not a first order. So this is how questions might be phrased, or this is how questions may be given to you. Okay, so I think this example now summarizes the integrated rate law for all the orders that we dealt with. Okay, so class rep, how much time do we have? Do we have how long can we have of this session?
50 minutes.
So you are occupied after 13 hours?
Yes.
Okay. Okay, then therefore let me just now stop here. I don't know when we are going to have another session, another makeup session, because I needed to also look at the last parts remaining, the half-life and also the effect of temperature. So I'll get advice from the class rep. For today, I want to end here. So today we have finished the integrated rate laws. So the next thing I want us to look at is the half-life. So each order of reaction has got its own formula for the half-life. Okay, the half-life basically is the time that it takes for the concentration initial to decrease by half. So sometimes you might need to use the half-life to also know the order of the reaction. Okay, so
there's a question.
To end here, class rep, you advise me. Yes, yes.
So there's a
Quickly, I
concern.
have 2 minutes. The session will close.
You always record these classes, but you don't share the videos. Why?
Yeah, it's for the sake of people not missing classes. Sometimes I'll share them at the end. All the videos, I'll share them at the end. It's for a reason. Once we are done with everything, then I'll share all the videos. Because I want to encourage people to attend classes, not just miss them out. Because it's online, they know that they are going to receive videos, so they'll deliberately miss out classes. So it's for a reason. I think I've answered that question. Exactly. So those who attend classes will benefit, yes, more. Okay, so we end here. The class rep will advise me when we can have another session. Okay, have a good day. not even share. Where the lecturer in China, oh, there's a lot of sharing. Well, banana, lecture slides, so. No, if I give you the lecture slides, you will not